Hey there, Mr. Weaver here, and this is Topic 8, Lesson 6, Vertical Motion Models. After this lesson, you need to be able to write a quadratic function using the vertical motion model, and you need to be able to identify and interpret key features of quadratic functions in different contexts. You'll know you're successful after this lesson if you can use the initial velocity and initial height to create a vertical motion model, and if you can identify and describe the meaning of the different quadratic features based on the context. Quadratic functions can be used to model different situations in real-life scenarios. One of those is vertical motion, or essentially when an object is flying through the air. Mathematicians and scientists developed an equation where if you can plug in your initial velocity and your initial height, then you can figure out how long it takes for the object to reach certain points and the height that it's at those times. This is all based on gravity. This was called the vertical motion model. The vertical motion model is h of t equals negative 16t to the second power plus v sub 0 t plus h sub 0. And this is the basic one we're going to use when objects are moving through the air. In our equation, we have v sub 0, which is your initial velocity, and h sub 0, which is your initial height. Those two things will be somewhere in the problem, and we're going to plug them in to the equation so that we can graph it or determine information from it. In the vertical motion model, every point is t comma h. So instead of x and y, t and h, where t is the time and h is the height at that time. So when we graph it, our coordinates are going to be time, comma, height. And that's going to be important to figure out how long it took an object to get to a certain height or how high an object is at a certain time. Let's look at some examples of vertical motion. A diver jumps off a 30-foot high platform at an initial velocity of 16 feet per second. What quadratic function represents the height h of the diver after t seconds of the dive? So if you can imagine, if we were looking at the side, the diver jumps up a little bit and then starts to fall towards the water. First, we need to write our function for our vertical motion. We're going to use that equation and then figure out what the initial velocity and the initial height are. It tells us that they jumped from 30 feet at an initial velocity of 16. So we're going to plug those two in. Initial velocity, it tells you initial velocity, that's going to go where v sub 0 was, while 30 feet high is where they started. So our vertical motion model would be h of t equals negative 16t squared plus 16t plus 30. Notice the leading coefficient for this is always going to be negative 16. Now that we know our function, let's graph it and figure out what each of the features mean in context. You can use Desmos and graph to find the features a little easier. Here I'm going to use my drawing that's not to scale to show where each thing would be while using the real values. So what would the vertex mean in context? The vertex is that highest point that it reached. So from this function, it's at 0.5 and 34. What this would mean is at 0.5 seconds, the diver reached a max height of 34 feet. So it took half of a second for the diver to reach its highest point. Next, what would the y-intercept mean? The y-intercept is where it crosses the y-axis. That is at 0:30, or just 30. That's saying that the diver started at 30 feet. So in context here, the initial height is the same as the y-intercept. And our zeros, where our parabola crosses the x-axis. So in this case, for our model here, it's at negative 0.958, comma 0, and 1.958, comma 0. Those are the points where the diver reaches the water, where there's 0 height. And it is at 1.958 seconds. What about the other 0? Well, that 0 to the left of where we started, that would be if the diver went back in time. Now, that doesn't make sense in this context, so we are not going to use it. We can't figure out the height of the diver at negative 0.958 seconds. It does not make sense in this context. Now it's your turn. Pause the video, write the function for the frog jumping off a leaf, and interpret what each of the following features mean in context. Let's check. You should have got this as your function, plugging in 3 feet as your initial height and 24 as your initial velocity. You should have got 0.75 and 12, meaning that at 0.75 seconds, the frog reached a maximum height of 12 feet. Your y-intercept, where you started, was at 3 feet, so the frog started at 3 feet. And the zeros, again, we have one that is negative and one that's positive. So in this context, only the positive one makes sense. 1.616, comma 0, meaning the frog reached the ground, or no height, at 1.616 seconds. Let's look at another example where we want to know some different information. A toy rocket is launched from the ground. The height of the rocket in meters is approximated by the equation negative 16t times the quantity t minus 8, where t is the time in seconds after it's launched. What is the initial velocity of the rocket? Here, it gives us an equation, and that is how we can figure out the height. So if we were to take that equation and plug in t, we can get the height. Well, we need to figure out what the initial velocity was. If it was written in the other format, where it was negative 16t squared plus v sub 0 t plus h sub 0, then we could easily just look at the number that's in front of t and take that as our initial velocity. So here, if we distribute out that negative 16t, we're going to put it in our standard form. So we would get negative 16t squared plus 128t. Now that it is written like this, we see that plus 128t. That 128 is the initial velocity. So our initial velocity was 128 meters per second. Now, for the maximum height that the rocket reaches, we need to find the vertex. In Desmos, if we type in our function, we can find the vertex, which is at 4,256. That 256 is your height of the highest point. So 256 meters must be the maximum height of the rocket. Now it's your turn again. Pause the video, figure out the initial velocity and the maximum height of the kangaroo. Let's check. You should have found that the initial velocity was 16 meters per second and the maximum height was 4 meters. For the initial velocity, if we take our original equation that we started with and multiply it out to reveal a different structure, we end up with negative 16t squared plus 16t, and that value in front of t, 16, is your initial velocity. In both of these situations, there is no initial height because both the rocket and the kangaroo started from the ground, so they started at 0. And then for the maximum height, it is at 4. Again, if we graph it on Desmos and find the vertex, we would find that the height in the vertex is 4. Let's look at another example. A baseball player throws a ball at an initial velocity of 35 feet per second from a height of 6 feet. Write a function that can be used to model this situation. So throwing the ball through the air, that is vertical motion. We would just plug in our initial velocity and our starting height, and we would get h of t equals negative 16t squared plus 35t plus 6. Describe in words the meaning of h of 4 in this context. H of 4 would mean the height of the ball at 4 seconds. If we were to evaluate it and plug in 4 to the equation, h of 4 is negative 110. In this situation, that would mean the ball is below ground, so at that time, the ball must just be on the ground again. In other situations, it might be below the surface. But in this one, since the ball is reaching the ground, it would just be sitting on the ground. After how many seconds does the ball reach its maximum height? So the maximum height is found in the vertex, and if I want to know how many seconds, I'm going to find the time that it takes to get to the vertex. So the vertex is 1.094, 25.141. That first number is the time that it took to get to the maximum height, 1.094 seconds. That would be when it's at its maximum height of 25.141 feet. Another way that you could find this is by using the axis of symmetry. Now, we learned in lesson 4 that the axis of symmetry is that imaginary line that divides the parabola in half. But it also goes through the vertex. And it goes through the vertex at the x value. So in this case, it would be at our time. Well, without graphing this, there is a formula that you can use from the equation for the axis of symmetry. It is the opposite of b over 2 times a. So if we take the values from our function, negative 16 and positive 35, and plug them in, I would get the opposite of b, negative 35, divided by 2 times negative 16, so negative 35 divided by negative 32, and you get 1.094, which is the time that it took to reach that maximum height. So you can do it either way. If you want to continue finding the vertex, just know the first value is your time, the second value is your height, or you can try using the axis of symmetry. Our next two questions deal with domain and range. So what is the domain and what is the range in this context? So domain is your x values. In this case, it's not x, it's t. So domain is the time in seconds. That's the value you're plugging in. You plug in the time, you get out the height. Which means the range then is the height, as that is what you get out. If you're not sure, think about what is used in place of x. Here it's t. What is in place of y? That would be h. And hopefully that can help you out in keeping domain and range straight. Now it's your turn again. Pause the video and answer the following questions about the basketball in this context. Let's check. First, you need your vertical motion function, h of t equals negative 16t squared plus 23t plus 5. H of 1 would mean the height of the ball after 1 second. In this case, since h of 1 equals 12, the height of the basketball at 1 second would be 12 feet. So it must be still in the air. How many seconds does it reach its maximum height? You should have found 0.719 seconds. That's when it's at the maximum height of 13.266. For the domain and range, domain again is time in seconds, and the range is the height of the basketball. Now let's look at one other application of quadratics that is not involving vertical motion or an object flying through the air. We're going to look at models with area. So a company builds rectangular pools that are twice as long as wide. Each pool includes a 4-foot wide deck around it. So here's our pool. If it's x wide, then it must be 2x long. It's twice as long as it is wide. And the deck is 4 feet wide. So it's 4 feet extended on both sides and on the top and bottom. First, write the quadratic function to represent the area of the pool and deck. So for this, we just need to get it into a quadratic function where it's ax squared plus bx plus c. To do this, we're going to just multiply the length and the width as we did with polynomials and find the area, even though we don't know what x is. So we do know that it extends 4 feet on the sides, so the length of it would be 2x, and then plus 4 plus 4, so 2x plus 8. Its width would be x plus 4 plus 4, x plus 8. Now to find the area, I'm going to multiply length times width. So multiplying those two binomials out, we would get 2x squared plus 24x plus 64. That is the area of the pool and the deck. If Carolina wants her pool to be 15 feet wide, what is the area of the pool and the deck? One way we can do this is, now that we know that she wants her pool to be 15 feet wide, we can just plug in 15 for x and multiply it out. So 2 times 15 plus 4 plus 4 times 15 plus 4 plus 4. Essentially, the pool and the deck would be 38 feet long and 23 feet wide. We can multiply that out and get 874. Or, since we just found the quadratic model for that area, we can use that function and evaluate f of 15. So you can plug in 15 every time you see x, and you end up with the same value, 874 square feet. Now it's your turn. Pause the video one last time. Answer the questions regarding the rug. Let's check. You should have found that the quadratic function was 4x squared plus 30x plus 36, and the area of the rug is 1,872 square inches. To get that, we would know that the length of the rug would be 4x plus 6, so it's 4 times as long plus 3 on each side, and then the width would be x plus 6, and if we multiply that out, we get our quadratic function. As for the area, if you take the quadratic function and evaluate it at 18, you get 1,872. So there's another example of how quadratic functions can help us in a real situation. There are other contexts as well. These are just a few of them. In this lesson, we learned mainly about vertical motion and how it's represented by the function h of t equals negative 16t squared plus v sub 0t plus h sub 0, where v sub 0 is the initial velocity and h sub 0 is the initial height. In quadratic models, the y-intercept is usually the initial height or the start value. The vertex tells you the maximum or minimum value and how long to get there. So in vertical motion, that vertex tells the time that it took to get to the maximum height. We didn't see any minimums. So for example, if the vertex was 224, then based on the vertical motion model, the object reached a maximum height of 24 feet at 2 seconds. We also saw zeros of the function, and those tell us when the object hits the ground, or equivalent, maybe it's water. However, in vertical motion, one of the zeros usually ends up being negative, indicating where it would be back in time. The exception to this would be if the object starts on the ground, then the 0 would be at 0, 0. No height, no time. And in those instances, there would be 2 places where the object is on the ground. So after this lesson, do you now know how to use the initial velocity and initial height to create a vertical motion model? And can you identify and describe the meaning of the different quadratic features based on the context? If you're not sure about these things, go back and look at the different examples and where the features were found and what they meant in context. In general, most of the features are going to mean the same thing regardless of the context. So you can easily extend them to other contexts. And that's the end of lesson 6 on vertical motion models.